Hello everybody, welcome into another lesson. So today we are going to talk about vectors and their dot products. First, we're going to talk about the dot product itself. So I want to clarify something here first before we go any further. In future lessons, not today, there's something called the cross product, which looks like true multiplication, vector v times w. That is called the cross product. I would like to specify that that is not equal to the dot product. Not at all, not by a long shot. Because when you take a cross product, you get another vector. When you take the dot product, your goal is to get a scalar or a constant. So cross products we won't talk about today. We'll talk about those in a future lesson. For today, we're only talking about the dot product. So you have some arbitrary vectors v and w with their respective components. To find the dot product of two vectors, you take the first component of the first vector times the first component of the second vector. You take that plus the second component of the first vector times the second component of the second vector, and you will get some number. You get a single number as opposed to a whole nother vector. So let's do some examples here. So vector v is 6, 3. Vector w is 2, -4. So we want to find the dot product of the two vectors. So let's go ahead and do that. And of course, it's denoted with a dot in between for the dot product. So you're going to take that first number in the first vector, 6, times the first number in the second vector, which is 2, plus you'll end up taking the second number of the first vector, which is 3, times the second number of the second vector, which is -4. So that's going to equal 12 minus 12, which is 0. So the dot product of vectors v and w is 0. And when the dot product of two vectors equals 0, that has a special meaning that we'll talk about a little bit later in the lesson. Alright. Let's do a couple more examples of just taking the dot product. Let's say we have vector v is -4, 1. Vector w is 2, -3. Okay, so we're going to take the dot product of these two vectors again. So you take the first number of the first vector, which would be -4, times the first number of the second vector, which is 2, plus take the second number of the first vector, which is 1, times the second number of the second vector, which is -3. So you should end up getting -8 minus 3, which would give you a dot product of -11. So the dot product in this case of vectors v and w is -11. All right, vector v is 5i plus j. Vector w is going to be 3i minus j. So we have it in linear combination form, which we know is the same as component form, just a different way of expressing it. So the dot product in this case is going to be that 5 times the 3 plus that 1 times -1, which would end up giving you 15 minus 1, or a dot product of 14. So the dot product in this case for vectors v and w is 14. So, okay, that's great. We found the dot product. Well, why the heck would you want to take a dot product? Well, believe it or not, we can find the magnitude of a vector using dot products also. So, if you take the dot product of a vector on itself, so you take the dot product of a vector on itself, that is equal to the magnitude of the vector squared. That equals the magnitude of the vector squared when you take the dot product of a vector on itself. So, in other words, finding the magnitude of the vector, you just take the square root of both sides. The magnitude of the vector equals the square root of the dot product of the vector on itself. That's how you can use dot products to find the magnitude of a vector. So let's do a few examples of that. So vector v is going to be 5, -12. So vector v is 5, -12. Let's use dot products to find the magnitude. So you'll take the dot product of v on itself, which would end up being that 5 times 5 plus -12 times -12, which is going to equal 25 plus 144, which is going to equal 169. Well, that's great. We got a big piece of it, the dot product of v on v, but to find the magnitude of v, you have to take the square root of that dot product. So the magnitude of v would equal the square root of 169, which is going to equal 13. So the magnitude of vector v is 13. And if we use the original formula to find the magnitude, which we learned a couple lessons ago, you would get the exact same result of 13. Let's do a couple more examples of finding magnitudes of vectors with using the dot product. So we have vector v is going to be 2, -4. To find the magnitude, that's going to be the square root. Well, let me write what we're doing. The magnitude of vector v is equal to the square root of the dot product of v on v. So in this case, that's going to be the square root of 2 times 2 plus -4 times -4, which would end up equaling the square root of 4 plus 16 equals the square root of 20, which would simplify down into 2 times the square root of 5. That means the magnitude of vector v equals 2 times the square root of 5. And I got just one more, then we'll move on to something else. Alright, we have to have a linear combination, 6i minus 10j. So vector v equals 6i minus 10j. Okay, so let's find the magnitude of vector v using the dot product. So that's going to equal the square root of v on the square root of the dot product of v on v. So that's going to equal the square root of that 6 times 6 plus negative 10 times negative 10. So that's the square root of 36 plus 100, which would equal the square root of 136, which should break down rather nicely now. Let's see if we can do that. Yep, it'll break down to the square root of 4 times the square root of 34, which would simply be 2 times the square root of 34 for the magnitude. So that gives you the magnitude of vector v is 2 times the square root of 34. Alright, so we've used the dot product to find the magnitudes of vectors. We can also use it to find the angle between two vectors. So if you wanted to find the angle between two vectors, the formula for that is the cosine of some angle theta in between the two vectors is equal to the dot product of the two vectors divided by the product of their magnitudes. So then you would, of course, once you get all that, you would take the inverse cosine and come up with your angle. So let's find the angle between a few vectors here. So let's say we have vector v is negative 1, 0. Vector w is going to be equal to 0, 2. Alright, well, I think it's pretty obvious that the magnitude of v in this case is just going to be 1. The magnitude of w is going to be 2. Come on. So we know the magnitudes. What about the dot product? Let's go ahead and take that. Well, that's going to, of course, then you'll end up getting negative 1 times 0 plus that 0 times 2, which would end up giving you 0 plus 0, which is 0. So in the end, you'll get that the cosine of theta is going to equal 0 because you'll get 0 divided by 1 times 2, which is simply 0. Well, theta equals the inverse cosine of 0, which we know would be 90 degrees. So in this case, these two vectors are what's called orthogonal or perpendicular because they have a 90-degree angle between them. And we'll do a couple more finding angles between vectors. So let's do that. We won't make it so easy this time. Alright, vector v is 4, 4. Vector w is negative 2, 0. Okay, so I think first let's actually go for the dot product. Let's kind of work in order from top to bottom. So let's go for the dot product of vector v and w. What does that equal? That's going to be 4 times negative 2 plus 4 times 0, which would give you negative 8 plus 0, which would end up being negative 8. So the dot product of the two vectors is negative 8. let's go ahead now and find the magnitude of vector v, which we know is the square root of the dot product of v on v, which is going to equal the square root of 4 times 4 plus 4 times 4, which would end up equaling the square root of 16 plus 16 equals the square root of 32, which would simplify into 4 times the square root of 2 for the magnitude of vector v. Alright, now vector w, that one should be pretty obvious because you have a 0 entry. If you have a 0 entry in a vector, then the magnitude, of course, is the absolute value of the non-zero entry, so the magnitude of w is 2. Now that we have all these pieces, we can go ahead and solve and find the angle. So the cosine of theta equals that dot product of v and w, which is -8, all over the magnitude of v, which is 4 times the square root of 2, times vector w, the magnitude of that, which is 2. Which is going to equal -8 over 8 times the square root of 2, which would give you -1 over the square root of 2. So that means that theta is going to equal the inverse cosine of -1 over the square root of 2. Alright, well, if we're taking the inverse cosine of a negative number, that tells us we'll be in the second quadrant, right? Okay, well, we can get an exact value because let's pretend that's positive 1 over the square root of 2. What angle gives you a cosine of 1 over the square root of 2? A 45-degree angle, right? But since it's in the second quadrant, we got to take 45 from 180. You'll get 135. So theta, the angle between these two vectors, is actually going to be 135 degrees in this case. And I got one more, and then we will move on to something else. Alright, so we have vector v is 2i minus 3j, vector w is I minus 2j. Again, we want to find the angle between these two vectors. So let's go for the dot product of v and w first. So that would be 2 times 1 plus -3 times -2, which is going to end up giving you 2 plus 6, which would equal 8. So the dot product of v and w is 8. Okay, let's find the magnitude of v. That's going to equal the square root of v on v, which the square root of the dot product of v on v, which would end up being 2 times 2 plus -3 times -3, which would end up being the square root of 4 plus 9, or simply the square root of 13. So the magnitude of vector v is the square root of 13. Now let's find the magnitude of vector w. So that's going to be, of course, the square root of the dot product of w on w. So that's going to end up giving you 1 times 1 plus -2 times -2, which would be the square root of all that. So you get the square root of 1 plus 4, which would simply be the square root of 5. So now we found both magnitudes and the dot product, we can go ahead and find the angle. So the cosine of theta is going to end up equaling that dot product of 8 over the square root of 13 times the square root of 5, which is going to end up equaling 8 divided by the square root of 65. So that means theta equals the inverse cosine of 8 over the square root of 65. So now we should be able to get an approximate angle value for that. And it should be in the first quadrant since we're taking the inverse cosine of a positive angle. Okay. So the square root of 65, now take 8 and divide it by that answer. Now take the cosine inverse of the answer. You get an angle of approximately 7.13 degrees. So theta, which is the angle between vectors v and w, is approximately 7.13 degrees. Alright, so we've also found the angle between vectors. Now we need to go on to discussing parallel or orthogonal vectors, or are they neither? So let's talk about that. So two vectors are what's called orthogonal. Another name for perpendicular. They mean the same thing, but in the world of vectors, the term orthogonal is preferred. Just know that it means the same thing as perpendicular. That's if you take the dot product of one vector times the other vector and it equals 0 and only 0, then the two vectors are orthogonal. Now, what about parallel vectors? So, let's say you have some vector v that has components a and b. And then you have some vector w that has components ca and cb. The idea is that if two vectors are scalar multiples of each other, but they have the same components on the inside, then they're parallel. So with w, we can definitely factor out a c times vector ab. So that means we can fundamentally say that vector w equals c times vector v. Or on the flip side of that, we could say vector v equals 1 over c times vector w. You could say either way. As long as one's a scalar multiple of the other, then the two vectors are parallel. If they're not scalar multiples of each other, and if the dot product does not equal 0, then they're neither orthogonal nor parallel. So for what we're about to determine for the next few exercises are these vectors parallel, orthogonal, or neither? So let's see. We have vector v has components -12 and 30. Vector w has components 1/2, -5, 4. Alright, well, it doesn't matter which route you want to go first. Do you want to see if they're parallel, or do you want to see if they're orthogonal? Choice is yours. Personally, I'm going to go for orthogonal first. So that means let's take the dot product of the two vectors. So that's going to equal then that negative 12 times that positive 1/2 plus that 30 times that negative 5/4. Okay, so that would end up giving you negative 6 minus 150/4 or minus 75/2, which would give you a dot product of negative 87/2. Well, definitely not orthogonal. There's no way they could be because the dot product isn't 0. So we know they're not orthogonal. So what about parallel? We still have to rule that out. So vector v equals negative 1230. Well, here's the thing. Can we factor out anything in common between the negative 12 and 30? There's a factor of 6, isn't there? We could factor out a 6 times the negative 2,5. But can we do something similar with vector w? Well, let's look at vector w. That's going to end up being the vector of 1/2 negative 5/4. Okay. Well, it might help if we got rid of the fractions. For example, what if I multiplied the vector by a scalar 4? So if I take 4w, I'll end up getting 2 negative 5. Well, look at negative 2,5 and 2 negative 5. That you could definitely factor out a negative 1 and get the negative of negative 2,5. So we have here that, let's see, so v equals 6 times the vector negative 2,5. So that then means that 1/6 of v itself would equal negative 2,5. And then you would have 4w equals the negative of negative 2,5. So if I divide both sides by negative 1, I'll get the original negative 2,5. So that means then that 1/6 v equals the negative of 4w. So that means that vector v equals negative 24 times vector w. Alright, so we have now shown that one vector is a scalar multiple of the other, so they are parallel. We do have two parallel vectors because they are both scalar multiples of each other. Okay, so that's one there for determining parallel or perpendicular. Alright, so what about this one? 3/4 for vector v. So 3/4 negative 1/4. And then what about, let's see, we have vector w, which has components of 5, 6. Well, let's go for their dot product first to see if they're orthogonal. So that means we'll take the dot product of vector v and w. Well, that's going to give you positive 3/4 times 5 plus the negative 1/4 times 6, which would end up equaling 15/4 minus 6/4, or for the final result would be 9/4. Well, the dot product doesn't equal 0, so they're definitely not orthogonal. Now what about parallel? So vector v is equal, of course, to 3/4 negative 1/4. Well, we can definitely factor out a common 1/4. So that would be 1/4 times the vector components of 3, negative 1. Alright, so that's great, but what about vector w? Vector w has components of 5, 6. Well, 5 and 6 don't have a prayer factoring, not whatsoever, so these aren't even parallel. They are neither in this case. So these two particular vectors are neither orthogonal or parallel. All right. Let's see here. What if we did vector v is equal to 8i plus 4j, and then vector w is going to be equal to negative 2i minus j. Okay, well, let's see if we can get these to be orthogonal. So let's take the dot product. Well, that's going to end up being 8 times negative 2 plus 4 times negative 1, which would give you negative 16 minus 4, giving you a dot product of negative 20. They're clearly not orthogonal. What about parallel? So vector v, of course, is 8i plus 4j. Well, do we have anything in common that'll factor out? We have a common 4. That would be 4 times 2i plus j. And then we could say that vector w, well, vector w is negative 2i minus j. The only common thing we can factor out here is a negative 1, but that should be all we need, because you'll end up getting negative 1 times 2i plus j. So v equals 4 times a vector, so that means 1/4 of vector v is equal to, okay, w equals the negative of the factored vector. So that means it would have to equal negative w. So that would have to mean then that vector v equals negative 4 times w. So these are scalar multiples of each other, so these are actually parallel. Last one of this here. So vector v is equal to 2i minus 2j. Vector w is equal to negative I minus j. Alright. So let's see if these vectors are orthogonal, parallel, or neither. So let's take the dot product of vector v and w. That's going to end up equaling that 2 times that -1 plus that -2 times -1. Well, what do you know? You're going to end up getting -2 plus 2, which is 0. The dot product does equal 0, so yes, we can stop there. These two vectors are considered orthogonal. So these two vectors are orthogonal to each other. All right. So that's it for this lesson. Next lesson, we're going to talk about projections of one vector onto another. So I hope everyone has a great night. Take care.